Good morning, it's Ecconia, and today I want to show you a really neat and small number display which I designed yesterday. It uses common practices which are known from other displays and probably also can be found in other YouTube videos, but I have not found a display which contains all the features which this display has. I got inspired by a CPU which performs quicksort. It's also on YouTube. I'm gonna put a link in the description. This is the display. It is stacked multiple tiles on multiple times on top of each other, and I just deleted that to have less room taken here, and I eventually gonna remove this whole CPU, but that doesn't matter at this point. So it's a really nice number display in terms of size, and it uses some really voodoo way of dividing a number into its own into its digits, because this is 10 digits. It's kind of hard to see because there's like useless lamps in between, but my display doesn't have that. So besides that, it has a special feature, and that is negative numbers will turn yellow. I have the same feature in my display, just that I turned it red for now. It's easy to change later on. So back to my display. I tried to discover that, to take apart that display over there, which I showed you, and I found some neat techniques. Besides the digit splitting, which I did not use, I found the dictionary, which is basically binary representation of each segment or each digit, how it's printed. Such a dictionary is explained pretty well in some other video. Anyway, I'm gonna link that too. This is how it looks. It's like really not human readable. Here you can see two of the segments, or pixels in my case, and that's these two lamps. I'm not using that because I just use 7 segments in this display, but I have the freedom to put any pattern I want for any digit in there. And here we got the input, which would actually, or what we actually want to print. So we can just move the slider to let a different number turn on. Oh, that is hexadecimal. If you shift 10 times, it will attempt to print hexadecimal, which is apparently broken. But it works quite well. How does this work though? I mean, like, you got this crazy dictionary or a constant combinator with crazy values, negative stuff and so on. Normally, one would not understand it. For that, I made this little explanation thing, or example thing. So basically, for each pixel, we got one signal. In this example, I just have 4 signals. And these here are the bits in each of the signals. I got one of these solid fuel blocks for 0 and a lamp for 1. Currently, the first one is already loaded. Like, that would be, if we shift 0 times, we get the number 0 on this display. So in this case, it's just 0011. Whatever that may mean, it's just a combination of pixels to show. Let's just get rid of this one and get the next one. This is what we do by shifting, and we do shift here. So let's perform one shift, and there we go. We got the next number, which was in this row. So we also get rid of that one and take the next one. And this is how we take the information out of the dictionary. Well, the dictionary has one number for each signal, which looks really confusing if you try to, or if you attempt to read a binary number with bit information as a number. You probably won't understand that. But, well, it's not that difficult to generate it. I will check out the link in the description. It has a really nice explanation of how to do that, if you don't do the coding attempt, which I did. Anyway, I just saw a mistake, or I noticed a mistake in my hexadecimal letter A. This pixel bottom down here is not lit. So how to fix that? I did in my case a little script, and as you can see I was prepared. I already have it here, the cursor, and A. And this is the top row, then the one below, the middle row, and this one here is the bottom row. So all we need to do is just exchange that pixel with a 1 instead of a 0 and run the program again. Here you can see the binary representation of the number. It's 0, 0 is the first one, then comes 1, 2, until we here at F, which is 15. And that's, if I'm correct, 16 bits, the other half is not used. Factorio uses 32 bits in total, so this comes quite handy. So all we did was we just went to the very last segment, which is the one below here, and changed the letter A, which is probably that bit. But what does that mean for us? Well, it was the last one. This one is the last one. O, I named that alphabetically. So this script does its purpose. Here we got the last one, which is the bottom, and we're just gonna exchange that with a new number, and as you can see, the pixel is there. So if you're familiar with coding, this might be the better solution to actually import such a dictionary than creating it manually in Factorio yourself. But possible. Okay, so I hope with this it's understandable how this works. So it just shifts whatever entry you have there, or to be precise, we shift these numbers here. Each column is a digit, and when we shift we go to the next digit. Each row is one single segment, and I have 3 by 5 of them, so 15 or 16 it is. I have 16 lamps, 16 pixels, 16 segments. You can do less or whatever amount you want to do. The other one I showed in the beginning is, for example, 11 segments. But, well, this is just one digit. How to get multiple digits? And no, I will not show you a voodoo technique to do this. This is perfectly simple. Okay. Currently we're inserting nothing, so let's put a super example number 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. This is the example number. As you can see, it shows perfectly. But how do we divide it? Here we got a dictionary, here we got the shifter and the pixel area. But the S is now generated by this combinator, this arithmetic combinator, which performs modulo. So he takes whatever value is outputted from the first combinator and modulo 10s it. That means he discards everything except the last digit. So do all of these. What we have to do is, this one is a special one because it's the first one. What we have to do is, after this one, is just decide whatever value V used to be by 10 to get the new value. It means the first digit will be the next digit. We basically shift down the decimal number by 1, so that each digit has its corresponding decimal digit. And that is gonna be inserted into the modulo. However, this way of doing it, although it works perfectly, has one flaw. Let's first of all show you how it works. I'm not sure if you can see it, but it looks kind of moving, right? Let me show you in zoomed out. If we have this number as long as this and we turn it off, as you can see, it walks through from the right to the left side. However, if we go to, for example, like the final display and do the same thing, as you can see, it's quite instant. And the way to do that is quite easy. Instead of chaining the divider combinators with each other, which is exactly performing or causing the delay, you can just connect all the inputs of the divider combinators with each other. That has, however, a downside. The first one is the same, the second one is the same, the third one not. It performs division by 100 because it needs the third digit of the number. So on 1,000, 10,000, 100,000, 1,000,000, and so on. Oh, this is actually millions. I was wrong earlier. But that doesn't matter for now. However, this is an easy change. It just takes a little bit of effort because you need to put all the numbers in there and can't just copy paste, which makes editing later on quite difficult. But that should not be a problem if you're eager to have a good display, which is also compact. There are some cheaty ways of having an incremental number delivered along with it. There's no space in this display for that kind of play stuff. There's another downside. This is 0. This is also 0. As you can see, this 0 here has a bunch of extra zeros which normally make it much harder to read the number. So we don't want them. We want to get rid of them. How to do that? For that, we should check what this outputs. Well, it outputs nothing. Like literally nothing. There's no value here. So let's check the difference between 0 and 0. For that, I'm going to insert 1,000. There it is. At this point, we have 1 at the output, which then gets modulo to 1, 1 shift, first digit. The one back here has nothing. Or at the output, it has nothing, because the input is 1 and the output is obviously 0 then, because 1 by 10 is, well, 0. We shifted out of our visible range. So this 0 here has no signal at all. However, the signal here has 10. Modulo doesn't care for that 10 because it modulos 10, so only the lowest digit, which is 0, counts. However, the key point is we got a value here, instead of this 0, which has no value. Try it on a piece of paper if you don't understand it. I will not repeat that. However, how can we use that? We can just add another component into this, which is a constant combinator, which checks the output of the division unit, if it has a signal or if it doesn't have a signal, which is this condition, and then it will just output whatever its input was. I just need to fix the wires here so that you are able to see the result, and that is obviously the lamps are off. I just did that 3 times for example purpose. Obviously in the later and finished version you have it a bunch of times, and that is at each digit, except the first one. You always want to display the first one. So here you can see zeros which have not been, or digits which have not been adjusted, and here everything is properly. So we're just gonna increase the number until a point where it matters. Oh, and as you can see, it works perfectly with the new digits. It's just one constant combinator which you have to add to make this magic possible. Obviously, the first one must not have this, and if it has this, for convenience, you may want to put something like bigger equal 0, because then it just always forwards, instead of just bigger 0, because bigger 0 means no signal, no output. However, bigger equals 0 means there is a signal, so the number continues, so I output the dictionary onto this. There's another change from this version to that version, and that is that the dictionary moved. I have a bunch of times the same dictionary here in each of the digits, but space is precious and you want to remove that from this position, especially at the end here. You cannot put like these substations here, because if you want to stack these on top of each other, then you cannot place substations there without causing major damage to the optical whatever result. And in fact, it doesn't even fit there without corrupting the image. So we need normal poles, as you can see down here. So how to do that? Oh, that's quite simple. We just put the dictionary somewhere at the side, and connect it to the pole, which then just goes all the way until the end. And as you can see, there's nothing new here in each digit. You have the division by 10, the modulo by 10, the digit turn off thing, and the shifter to select which entry in the dictionary to use. But the sides are a little bit more pumped. Why is that? Okay, let's have a look. Let's put a really neat number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Works? Easy? No problem? Right. Okay. Minus. Damn it. As you can see, you cannot see anything. And why is that? To be honest, I don't know. The thing is that this is not made to handle negative numbers. And to be honest, I don't know at which point it fails. But the point is, we just want to convert all negative inputs to positive inputs. The circuit for that is quite easy, and there are a bunch of circuits to do that. Whenever the number is positive, we want to leave it unchanged, multiplication by 1. Whenever the number is negative, we want to invert it to get a positive number, which is multiplication by negative 1. For that, because we only need one side enabled, we put some decider combinators in front. In this case, it just checks if the number is bigger than 0, and then it outputs the number. And in the other case, it just checks if it's below 0, and then outputs the number. No voodoo magic, this is just printing the number and giving it to the first divider. Yep, let's put a number there which is negative, like this one. There we go, it works. But as you can see, there's a negative sign here, which you should add to your display, else things may get confusing if you want to display negative numbers. And it's quite easily done. For starters, I grabbed the input signal from here. I could have done it on this side, but here's a green signal and here at the bottom is a red signal. Here I can grab the red signal because if it's smaller than 0 or bigger than 0, no matter, I get the result, which is merged onto the red signal, so the red signal always contains whatever the input used to be. On the other side, the red signal goes into this decider combinator, where we just do a normal negative check again and just output anything one time, so that the lamps will trigger and turn on. So if the number is positive, this will not output anything, the negative sign will be off. So there is also no voodoo magic here. Yeah, so this already is a really small and easy display which you could use if you don't want colors. However, you want colors, you need to put a little bit more extra effort. As you can see, there's a bunch of more combinators here, especially on that side. There's one more thing to watch out for when you use this type of display as is. And that is, if you have a negative number, there is some synchronization problems. If you turn this off, you may notice that the negative prefix is a bit faster than the rest of the digits. So what you need to do is to just put a little bit of random delay here, as I did in the finished type of display. Here you just got a combinator which does nothing to the value, and that just causes a 1 tick delay, or one whatever that U stands for. Unit probably, or update, 1 update delay. So it's 1 update delay. But how to handle this? I tried a lot of attempts to get it small and do it in a neat way. However, this is my finished version. In this version, I just grab the signal from the combinators, because this one is only activated if the number is positive, and then I output a Y, and it really just checks for positive, and this one just checks for negative. I could connect these two with each other, but there's no purpose to that, because these already do the same check. So these here also have, beside a conversion, also a delay purpose. One could make it smaller, but there's no point in it, because you need the delay. So we got for negative numbers a Z, and for positive numbers Y. Preferably I would use P and N for that, but I can't for the simple reason that that at least n is used in the display or in the segments here. I believe it's this one. Yeah, right. There is n, so I cannot put n onto the same pole. That would clash because the dictionary is also transmitted over the poles and it also contains the n. So this just gives us y or z where the number is positive or negative. All the other magic happens over here, while it is not really magic. First of all, let's turn on the colors. As you can see, it's perfectly possible to turn on or off the colors on the fly while the thing is running, and it doesn't bother. It's not bothered by it at all. What this does, okay, that is kind of irritating because colors have the tendency to make the whole number blurry, which is kind of a thing which Factorio should work on, in my opinion. It's nice to have intensive colors, but it's bad for readability, really bad. Anyway, we got our Z or Y signal on this pole, on the red line, which goes over to these two. Well, these two is nothing, and they have on one side a delay purpose, but on the other side a filter purpose, because they will not let anything pass which is not Y or Z. And on the red wire I also have the colors. If you notice it, the red wires are connected to all lamps, and like literally all of these lamps are connected by the red wire to transmit a color, in case that there is a color. I could transmit any color at this point. For example, I just go here and turn the color to yellow and 1, and then it's yellow. Constant. One could also change the value here and undo this so that it works properly. But, well, let's just go back to this way because it's more customizable. Anyway, after filtering, we put the value to the decider combinations, which just check if the flag is set or not. So if it's set or if it's Y, negative or positive, or if it's not. It doesn't do much else. And when that's the case, it just forwards whatever the constant combinators contain, or not whatever, but the particular signal, which is red or green, onto the red signal back again. And that is why we need these two filters, because the colors are on this side and they must not be on that side, on the top side. I could just connect this, but then the color would just loop itself and keep being stored constantly, which is kind of really horrible. Anyway, don't do that. So here are the filters, and yeah, so much for that. What is that one for? This one just is a negative check, or checks the negative flag, and just outputs any signal. Why is that? It's because we can toggle the color for negative, and this one just listens to anything. So it only one side listens to the red signal, but also to Z signal, and currently there is no red signal, so it needs some other signal to listen to, and that is just this Z one. It's not in the way if we turn on colors, because then it still listens to either of the signals, doesn't really matter. And that is how the whole thing works. If something was not understood, just leave a comment, and I'm gonna try to put a blueprint somewhere for other people to use this display, because it's really compact, has negative and positive colors. By the way, colors. I should maybe show the positive color too. Not that it matters, and I will probably not use the colors in the final whenever I use the display, but it doesn't really change much of the size of the display. And as you can see, it's perfectly synced. There's like no way of having any white in there when it's supposed to use colors, and it's really smooth and works fine, whatever. So much to this morning recording. Yeah, that's a display. Have fun, feel free to use it, and if you want to, leave credits. However, it just uses common logic, nothing special in particular. Thanks for watching.